Team, now we're going to be talking about LC circuits, inductor capacitance circuits. And in this one, it is basically an energy problem. It is asking us to solve for the charge that was stored at the capacitor before the switch was closed. And it was also giving us the maximum current through the circuit. If you read more into it, it says the ideal inductor is given to us. That says two things. First of all, it says that in our assumptions, which are important for this problem, no energy is dissipated because we have an ideal inductor. This is perfect because we don't have to worry about any work being disappearing, any energy disappearing from the system. And then it also says that there is a maximum current, and whenever there's a maximum current, it means that the maximum current is incurred at the inductor. If we have maximum current, we have maximum energy. And therefore, we can use our equation for the electric potential energy in the inductor, which is I max squared times L over 2. And this is denoted in this equation in the PRC as well, because it is saying the maximum current. That is why we can use this equation. Now, so we have a capacitor and an inductor in here. And I know that Nate was talking about, in the last class, was talking about, we have the total electric potential energy in the system, which is UC, which is the energy stored in the capacitor, plus energy stored in the inductor. And we will call this step 1. However, the total electric potential energy is equal to only the electric potential energy of the capacitor before the switch is closed. Because at this point, there is no current traveling through the circuit because the circuit is not open. Therefore, there is no current going to the inductor. The only electric potential energy that is available is coming from the capacitor, not the inductor. But once we have max current, when current is at its max, it means that, let me put it right here, current is at its max. It means that the total electric potential energy is equal to the electric potential energy of the inductor. Therefore, because current balances out, and let's focus here, current goes from the inductor to the capacitor, and they're both in resonance. So going here and traveling back, and so on and so forth. It means that we never have, and another thing is that since energy is not dissipated either, we can go and say that UL, which is the inductor, minus UC, which is the capacitor, equals 0. Because always one will have the max, and then it goes back to the capacitor, and the energy is never dissipated, so there's no difference between both energies. Therefore, the subtraction of both of those will equal to 0. Okay? Because they will equal to 0, the energy in the inductor equals the energy in the capacitor. And we can solve for now just plugging in the equations of 1 over 2 L squared, or L times L times current max equals 1 over 2 times charge squared over the capacitance, and that all will equal to charge, the square root of inductance times the current max times the capacitance. And that will have the answer for you for the charge in the LC circuit. Important things. Just remember these amazing equations that you have here. You may remember that since it is an LC circuit only, and if it's an ideal circuit, if it says ideal inductor, you know that, hey, there's no energy loss, therefore the energy in the inductor will equal the energy in the capacitor. Okay, so that is one way of doing it. There's another way. This is solution 1. And solution 2 is thanks to Maggie, because Maggie brought this one out. Solution 2. This is the equation for charge when there is an AC circuit, when there's an oscillating current. And because that is the equation, we can also find out current if we derive the equation for charge. Now I know, like, my goodness, deriving charge with respect to time. That sucks, right? But if you are able to derive it, then I of t will equal negative angular frequency times initial charge, right? Because that is the calculated charge of the capacitor, times sine of angular frequency times time plus the phase angle. Now, when we're talking about the max current, because it is saying like we have the max current. At max current, sine of angular frequency times time times the phase angle will equal plus or minus 1. Because in a sinusoidal graph, it goes like this, right? If at this point right here, it is pi over 2. At this point right here where it's max, and let me put this as current, it is 3 pi over 2. If you substitute this to pi over 2, sine of pi over 2, that will give you the max current available at that point. Therefore, we have I of t equals negative angular frequency times charge. And since we have I max, because this is at this point is I max equals, or I max over angular frequency equals the charge. Let's leave the negative there. It doesn't need to be there, mind you. It doesn't need to be there. Whether it's positive or negative, it doesn't matter. But angular frequency, but they don't give you angular frequency. They do, because you have inductor and capacitance. And since it is an LC circuit, 1 over LC, inductor capacitance, will give you the angular frequency. Remember this equation right here? And this is for a resonant frequency. And at resonant frequency, that is what we see oscillating in an LC circuit, because there is no energy being dissipated in this circuit. Okay, this concludes my LC circuit review. Thank you.